Hello and welcome, Physics 1401. In this video I'm going to talk about forces, which is chapter 2 in our book. Now, in order to understand forces, you need to know what vectors are. And I'm not going to go into detail because there are two more videos, Vectors Part 1 and Vectors Part 2, which explain in detail what vectors are and how algebraically we add them and all that. And even more that we don't need for this topic today. But please refer to those two videos, okay? Vectors Part 1 and Vectors Part 2. I'm going to focus on forces today. Now, what do we understand from the word force in physics? Okay. Well, usually there are two meanings to it. The first one is sort of a contact force. You push an object, or you pull it, or when you're carrying your bag, it's sort of like pulling it, right? So these forces are really easy to understand, and we experience them daily. These are called contact forces. Okay, contact forces either push or pull. You can push an object or pull an object, or tie a string or rope or chain and pull the chain. It's still a force which is transmitted through physical contact. All right. And if you start thinking about ropes and strings and rubber, you know, it could be even elastic. Now you got to think about forces inside that medium as well, which we call tension. So let me include that here as in parentheses. Tension is the force in a rope or a string or a chain. Okay, now this is the most common understanding of what force is. But if you study the idea of forces theoretically, deeply, the fundamental nature of force, why do objects push each other in the first place, right? I mean, if you try to push air, for instance, right? I mean, you can't move air just by pushing it. You're going through air or liquids, okay? So obviously we're talking about solid objects here. Solid objects. But what about the deeper meaning, okay? I mean, what prevents when you touch an object, which is a solid, your hand doesn't go through it as it would when you're in air or water. So what is that force that keeps you or prevents you from going through the medium? Okay, what kind of force is that? All right, or when you have a magnet, all right, the magnet you put on your fridge, bring that close to the refrigerator, you feel the attraction already. Okay, you don't have to touch the thing. There's a force without contact. Okay, so something fundamental is going on there. So these types of forces are going to be called interactions or fundamental forces. All right, this is the second class of forces. These are called interactions. It's more than just physical contact because it can have an effect at a distance. All right, so action at a distance, such as electromagnetic forces. Magnetism, the magnets I was telling you about. So electromagnetism or electromagnetic force is one of them. Electromagnetic forces. What else? Well, gravity. Gravitation. The sun attracts the earth 149 million kilometers away, but we still feel it, right? Gravity or gravitational forces. Electromagnetic force, gravitational force. So these are very famous two examples of interactions. Okay? Turns out that in nature there are only 4 of these forces. So 2 of them are electromagnetism and gravity. There are 2 more, add up to 4 in total. Let me just give you the names now and explain just a little bit. It's not really our topic today. The third force is called the strong force, or strong nuclear force to be exact. And the fourth one will be weak nuclear force. Now these 2 forces also act at a distance, but at a very short range. Okay? Electromagnetic and gravitational forces in principle all the way from 0 to infinity. Okay? So 2 objects could be this far and they will attract each other, believe it or not, gravitationally. We can't feel it, but it's there. And you take this, take it to the moon, it's going to still attract it. But the force will be so weak, even weaker than what it was right here. Okay? But the good thing is, gravitational forces are always attractive, so they add up. So when we think of the universe as a whole, like galaxies, stars, planets, the forces that govern this motion is gravity, not other forces such as electromagnetic force. Now, electromagnetic force is stronger than the gravitational forces because you can feel it. Bring a small magnet to near another magnet, you can feel the force right away, right? You can't do it with 2 ordinary objects. You can't feel the gravitational force. If you replace one of the objects with a huge object, well, even not a mountain may not be enough. It has to be a rock as big as the Earth itself, and then you will start feeling the weight of it. Okay, so you have to have a lot of mass in order to feel the gravitational forces. But in the case of electromagnetic forces, 2 small magnets can demonstrate this interaction easily, right? So electromagnetic force is many times stronger than the gravitational force. But why is electromagnetic force not the dominant force in the universe, meaning the motion of planets and stars and galaxies is not governed by this force? It's because there is a polarity. The force comes with flavors, or 2 types. It could be attractive or repulsive. When you play with magnets, actually you will see. You rotate the magnet the other way around, it'll start pushing each other. They will push each other as opposed to attracting. This is because of this polarity issue. We have north and south poles of a magnet. Or if you just think of electric charges, which is within the electromagnetic interaction, okay, half of it is magnetism, the other half is just electricity. Electric charges, or charged particles, like I'm sure you've heard of protons and electrons in an atom. Protons are positively charged and electrons are negatively charged. Now try bringing 2 protons together close to each other. They will start repelling, okay? But when you have a proton and electron, they will attract. Opposite charges attract, like charges repel. Turns out that on a large scale, like planet Earth or stars, you have equal number of positive and negative charges. So overall, those forces are balanced, okay? So it's only gravity who is responsible for those large-scale interactions. Although both electromagnetic force and the gravitational force in principle extend all the way to infinity in space, it's only the gravity that is dominantly responsible for any kind of motion on a large scale. So these two forces, on the other hand, are only short-range forces. Now it is strong, don't get me wrong, I mean this is the strongest of all. And what is it? Remember those two protons that you were trying to bring together? So you push them, let me draw it actually here. This is a proton with a positive charge, another proton, positive charge. Now these guys repel each other, they don't want to be together, okay? So you push them by force, you bring them closer, closer, closer. There will be a point after which they will start attracting each other, okay? Instead of repulsion, we will have attraction. That is the strong nuclear force, and that's why we have atoms in the first place. I mean, not only hydrogen atom, but let's say helium atom. Helium is made of two protons, okay? So think about the periodic table. If you've taken any chemistry class, all the elements in the periodic table have they have their number of protons in each element, okay? Basically change, you add one more proton, you go one step ahead or further in the periodic table, all right? That is a strong nuclear force, the force that binds those protons together. It's not just the protons, because we also have these neutrons. I was talking about the helium atom, right? So you have two protons, 1, 2, and then you have two neutrons, and for neutron, P4, proton. These are particles within the nucleus of an atom, but they are neutral, okay? Neutron has no charge, no electromagnetic force, okay? So electromagnetically neutral, those are the neutrons, but protons are pushing each other away, but all four particles in the nucleus are kept together in close proximity in the nucleus by this force, which we call strong nuclear force. And indeed, it's the strongest of all four elementary forces. We don't know of a fifth force yet, okay? There are only four fundamental forces in nature. And maybe you're wondering, okay, how come two protons attract each other? What is the source of this force? In order to understand it better, you have to know what's inside a proton, okay? Now, without digressing too much, keep in mind that a proton is not the smallest particle you can imagine. Actually, a proton is made of three small particles, which we call quarks. Okay, so the combination of these three is actually what appears to us as a proton. Okay, these are three quarks. They're not all the same type. There's a difference here. The quarks come in different types based on the way you combine them, but they're always three in order to make a proton. They're three. You can also make a neutron using different set of three quarks. So let's use the blue color here. Just to denote we're talking about a different particle. We're talking about a neutron now. So when these quarks are bound together, and the force that binds them together is the strong nuclear force, which we can show here as springs. Springs. You know what's interesting about springs? Okay, when you play with springs, you can compress them, or you can expand them, or push them away, right? When you do that, there's a force that you will feel. Or any elastic material. You stretch it, it wants to go back to its original state, okay? There is a restoring force there. In this case, that force is the strong nuclear force, okay? So a spring is like a representation. I'm not saying there are small springs between quarks, but these forces, this strong nuclear force acts like a spring. That's why you never see a quark by itself, okay? The quark wants to be with other quarks, all right? But the thing is, whenever you have another proton right next to it, so let's go back to our white color here. This is another proton just next to the first proton that I just drew here. So we have those springs again also here, there, and there. Now what do you think is going to happen between, let's say, these two quarks which are close? Don't you think there should be an interaction there? Yeah, I would assume, right? Why not? It may not be as simple as this, but I'm just trying to make a point here, okay? So the force that binds the quarks together is the same force that binds the protons together. That's what this means, all right? So that's strong nuclear force. You can break it. You can break it apart if you supply enough energy. That's how the weak force also comes into play. The weak nuclear force is responsible for radiation, okay, radioactivity. Now, it's more complicated. Let me just say a couple of words though. The protons and neutrons, they're made of quarks, different type of quarks, but still quarks. And it's possible to turn a neutron into a proton, all right? Or vice versa, depending on the case you analyze. And during that process, some other particles also emerge, and light particles also come out, and we have particles called neutrinos. They also show up, okay? So it's a very complicated topic, but pretty much if you've heard of radioactivity, like when you go to medical exam, some imaging, radioactive imaging, okay? Or think about other processes where we have nuclear interactions, even nuclear bombs and all that, okay? So these two forces are involved. But again, these are very short range forces. Okay, so without losing much time, okay, I'm gonna separate this from now on and not touch it, except for gravity. Gravity we will need, okay? So gravitation, I'm gonna talk more about it. It's so fundamental in understanding classical mechanics, which is basically physics 1401, all right? And you won't need to study electromagnetism until you do the second part of this class, physics 1402, or depending on the version, if you're taking physics with calculus, same thing. The second part will be about electromagnetic forces, but gravity will be still fundamental in this course, okay? But strong and weak forces, okay, you can just ignore it for a long time. We won't be doing anything, okay? So, going back to the idea of contact forces, remember when I said, okay, you push your, you move your hand in air, you go through air, but then you try to do the same thing. Let's say you have a flat surface, you push with your finger doesn't go through it, okay? I mean, there's a contact force here, but fundamentally, any force, which we call, whether we call it a tension, the force in a rope, or push or pull, on a fundamental level, it should be reduced down to one of these four fundamental interactions, because there's not a fifth out there, okay? There are only four forces. So which of these four forces is the one that is responsible here, that my finger doesn't go through that solid object? And the answer is, interestingly, the electromagnetic force, because that is the force that keeps the atoms and molecules together. That force is present in the case of air, gas also, but those atoms are far apart, okay? But in the case of a solid object, there's a structure to the material, very strong structure, and electromagnetism is responsible, okay? just like that magnet feels that strong force when it's attached to the refrigerator. The molecules that make up this plastic or metal or glass, anything, any solid object you can imagine, are strongly bound with electromagnetic forces. All right? So, how do we treat forces mathematically? Okay? That's the most important thing for us right now, because we know that physics is heavily based on mathematics. If you watched the first video last week, you've seen it, okay? We use math a lot, and we will be using math a lot. And the mathematical description of forces will be done with vectors, okay? So I talked about vectors in detail in those two videos I was telling you about earlier. I'm not going to spend too much time right now, so I'm assuming that now you know what a vector is, how you represent it on paper. You just draw an arrow, and a letter, maybe A, with a little arrow on top, represents an arrow, okay? And you know how to add vectors, meaning if you have another vector here, B, you basically parallel transport B near A, which means you bring the tail of this arrow to here, where the tip of A is, without changing its orientation, okay? So it has to remain parallel. So you bring it here. So this is still B, all right? The same vector. As long as I'm doing this on a flat surface, it's still the same vector, no matter how I move it. It's called parallel transport. And now I have a special lineup, right? It's called tail to tip, and then tail to tip again. So what I do is I start from the tail of this arrow, which is A, and I go to the tip of the second arrow, which was B, and I call this vector A plus B. All right, and A plus B is the same as B plus A. You can change the order. There's another way of showing this in a graphical manner. Instead of moving B here, you can move B right here. An alternative method, and this makes actually a lot of sense if you think about the component method, which is also in the video in part 2. Now we have this alignment where both vectors originate at the same point. Then what you do is you draw parallel lines to A and B. So you have this, and then you have that. These two lines are parallel to A and B. Okay, a parallelogram, that's what it's called, this four-cornered object. But then you go in the diagonal direction, like this. This arrow is the same as this one, okay? So they're both A plus B. And as I said, A plus B is equal to B plus A. So these are all in part 1 and part 2. Please watch those videos if you haven't already. And you can learn how to subtract vectors in this manner, or what does it mean to put a negative sign in front of the vector that flips the direction by 180 degrees, for instance. Okay, and how you would describe these vectors if you want to trace an object, a fly flying in your room. Okay, how do you trace its path using vectors? That's not the subject of this chapter, but still something good to know, which we will use later. Okay, but today I want to focus on the use of vectors for forces. Okay, and let me also summarize the idea of components. Any vector can be written as the sum of two vectors, and this is in part 2 of those videos. We call these the component vectors, and we give names x and y, or ax and ay, and these letters come from the Cartesian coordinate system, these two axes which are perpendicular to each other, and then you can place your vector right here, and the projection of this vector onto these two axes. It's also called a rectangular coordinate system because of this reason. You create small rectangles. So these are called the component vectors AX and AY. Okay. There's also the idea of unit vectors, which is also in vectors part 2. Just be careful though. In that video, I use the letters I, J, and K. Actually, I put hats on top of these and call them I hat, J hat, and K hat. These are the unit vectors. A unit vector is a special vector which has a certain length. Okay, a length means the length of the arrow. In principle, in general, the length of the vector can be anything, but when it comes to I, J, and K hat, the length of these vectors are all equal to unity, just one. Okay. Secondly, the direction of I hat has to be in the x direction, and J hat has to be in the y direction. And if you think of the third coordinate, which is out of that plane, z we call it, that's for K hat. Okay, so these are not arbitrary directions, but the directions of your axes. Now, in some books, including our book, they don't call it I, J, K. They just use the letters X, Y, Z again, but put a hat on them. Okay, so that's Z hat. Z hat is the same as K hat. I'm going to use them interchangeably. Please do not get confused. So how does this apply to, let's say, this one here? Well, AX is the length of A times those little I hat vectors. So I can write each of these component vectors as the length of AX, which I simply write by dropping the arrow on the top, times that unit vector, which is X hat. Same thing for AY. I could write it as AY times Y hat. Okay? So, this was a really short review of vectors, assuming you have watched those videos. If you haven't, please stop here and then go to those two videos, watch them. You don't have to spend too much time on how vectors are used when you trace objects, in 3D space. You can skip that part if you like, or you don't have. It doesn't hurt to learn, right? But make sure you brush up the unit vectors and how to add them, how to subtract them, okay? The graphical and component methods. When you add two vectors, say if you write B also in this manner, that will be bx x hat plus by y hat. When you think about a plus b, well, this vector will also have an x component, like, okay, if you like the notation, and that is nothing but ax plus bx. All right. So you add the components separately. Same thing applies to subtraction. If you subtract b from a, you're going to subtract the x component of b from the x component of x. All right. So how is my video, by the way? It's kind of getting dark here. Let me quickly check if the lighting is enough. Okay, I'm still seen here. All right, I don't need to turn on any lights. Now, let's go back to contact forces, our main interest here, okay? Push or pull, or forces within cables, ropes, strings, chains. And actually, let's add one more item here. Let's talk about friction also. Friction is type of a contact force. It's more of a resistance, okay? When you rub an object against another one. Let's say the box is too heavy, you can't lift it, you just want to push it on the floor. The floor will resist, okay? Unless you're doing it on ice, in which case there won't be too much resistance. But that resistance is also a force, at least for this course, okay? And we call it friction. So let's talk about each of these, all right? Okay, so I said represent forces as vectors. So if I'm pushing the object on the floor, this is the floor, and here's the heavy box that I don't want to lift. Okay, I'm just pushing it. So I'm gonna place a vector here and put a letter here, F. Okay, this means the force I'm exerting on it. Now, is it always going to be a horizontal force? Does it have to be a horizontal force? No. I could still do the job by pushing the object with a force with that angle here. Is it going to help me? Well, not really. I mean, let's call this angle theta. It's still F here. But I mean, I can still get the job done, but why would I push it downward? Okay, if you've experienced it before, I mean, it may create more friction, for instance. Or I may do the opposite. I may tie a string here and pull the string in this direction, okay? String or rope. Or one of those, what's the word? Bags, you know. So I could put my arrow here, right there. Now this is the force inside the string or rope, but it's still a force, all right? Call it F. Or, since it's tension, use a capital T and put the arrow again. T for tension. It's still a force after all, right? So that's our representation in our pictures when we're solving physics problems, okay? It always helps to draw pictures. And there's a special diagram that we draw, which is called a free body diagram. Free body diagram. It's kind of like this picture here, which is already simple, but there are some rules to this, okay? So rule number one, you isolate the object from its surroundings. That's where the word free comes, okay? So you don't have to draw the floor, for instance, okay? Do we have carpet or is it hardwood floor? Okay, how long is this? We don't care about any of those. We don't care. But by doing that, we have to introduce something else. Like in this picture, we know there's friction. If I'm pushing it to the right, okay, the resistance that the floor exerts on the object I'm moving will be in the other direction. If I'm pushing it to the right, and if it's moving in that direction, the resistance, which we called friction before, let's use red, the friction will be in the opposite direction. Okay? So I'm just showing it right there where the two objects are face to face, right? So this is friction. And let's use a small f to denote friction. Now, a free body diagram, I said, doesn't require the floor, but if I take the floor out from the picture, I have to keep something that represents what the floor was doing, right? And that is the friction force, right? So that's number one, isolating the object from its surroundings. Rule number two, only show the forces that are exerted on the object. I mean, all of these forces I drew here are the forces that are exerted on the object, okay? But think about it. I mean, the box is also pushing against the floor, right? Even if you don't do anything to the box is pulled downward by gravity, which means it's exerting a force on the floor, okay? If you have a hardwood floor and if you're putting your chair and keep sitting on that chair, okay, a month later you will see the marks on the hardwood floor, right? So there's some force exerted down there. So let me show it here. Let's use green. there will be a force here. Okay, what is this force? Now, this force could be the box pushing the floor down. But this force should not be shown in a free body diagram. Okay, that's second rule. So rule number one, isolate the object from its surroundings and just draw it here. And you don't have to draw the picture. I mean, if it's a toy car, you don't have to draw a toy car again. Just put a little square here. Okay, that's your object. Okay, we know. You've already isolated. Put a little circle. Okay, I don't care what you do, but you don't have to draw a picture really, as you would normally when describing a physics problem. On a free body diagram, just show it with a little square. It's okay. Then show the forces which are exerted on the object. That excludes this one. Okay, so do not use this. We're not interested in what happens to the floor. That would be the free body diagram for the floor. Yeah, well, in that case, you would have to worry about this force in green. But in our case, we only worry about what happens to the box. So only show the forces on the box, or shows the forces exerted on the object. Like, consider the string here and friction, for instance, at the start. So the string pulls it this way. This is our tension. Yeah, show this is fine. And then the friction, the red colored force. Now you can show it as a force that is just like this one, okay, like this. It's not wrong, but I suggest attach the arrow to the object in this manner. Okay, it's the same thing. It just looks better, all right? Just looks better. This is F, this is T. And there's one thing we shouldn't neglect, which is always present. Earth pulls the object downward. So Earth exerts a force on the object as well, right? That is what we call weight of the object. So here this object is pulled downward by its own weight. Earth pulling it downward. Include that. Weight. Alright. Now, is the free body diagram complete? No, there's one more thing. You will need a coordinate frame. Okay, X, Y, those Cartesian coordinates. And you can draw them any way you like. Those two axes, X and Y, as long as they are perpendicular to each other. Anyway, meaning, well, this is also perpendicular, right? So, this is not better than that, or worse than that. They're both correct. But depending on the problem, sometimes it's better to use one of them. It's easier, okay? It just depends on how many forces are involved and how many of them already line up along the Y and X axes. So for practical reasons, you may prefer one of them over another, okay? Now in our case, we have 1, 2, 3 forces, and 2 of these forces, namely the friction and weight, are already lined up in the X or negative X, right? This is negative X, this is positive X, this is positive Y, this is negative Y, are already lined up in the negative X and negative Y directions. So why don't I use this one, all right? As opposed to the one with rotated coordinate frame. Okay, maybe if I had used this one, yeah, the tension force would be lining up at X, but then W, weight, and friction, F, would have components, non-zero components, let's say. Okay, so it's just simpler to me. So if you do that, please include the angle also here, this angle. I don't know what we called it. Well, let's say it is alpha. Alpha. And put an X here and Y there. All right. So that is the free body diagram. Usually there's one more component to free body diagrams. We're not going to talk too much about that today. That is when objects move, they can speed up, right? Or slow down. Or we can move the object with a constant speed in one direction. Okay, you have possibilities. But if it is speeding up or slowing down, you should also show it in a free body diagram. But I'm not going to worry about it today, okay? But that's the final component of a free body diagram. Now, why do we go from a picture like on the left to the free body diagram? Because once you draw your free body diagram, you've pretty much a third done with the problem, okay? So every problem in physics pretty much will have 3 steps, and this is the first step. First step. There are 2 more steps. So step number 2 and step number 3. 2 and 3, let's start with 2. We have physics laws, specifically Newton's laws of motion. So let's write here, Isaac Newton, one of the most famous physicists ever lived, right? Isaac Newton and Albert Einstein, and you pick the third, but these 2 are the most famous, right? Newton's laws, and I'm going to talk about 2 of these laws. There are 3 in total, okay? So you apply the laws, and most of the time the second law actually, and then you're 2/3 done with the problem just by writing the Newton's law. But when you write it down, you use the free body diagram. That's why the free body diagram is so important. That's the first thing you do in the beginning, okay? And then you apply Newton's law to your free body diagram, and you obtain an equation of motion, if you will, okay? Even if the object is not moving, you end up with an equation, okay? But that comes from Newton's law. What is step 3? Well, if you have an equation, what's next? What's left to do? Solving the equations, right? Do the math. So, do the math, which means solve the equation from step 2. Okay, the 3 steps of solving a physics problem, pretty much. I mean, it applies to many problems. I'm going to show you examples of that, okay? So that's why a free body diagram is needed. So I already actually talked about forces with components, such as this one, and then the tension force. Forces in springs called tensions, and the friction force, okay? Now, the friction needs to be explained, okay? I will do that. This tension is not that mysterious. Just keep in mind that if you consider little portions of that string, each little portion carries that force, okay? So it's not just the part that is attached to the object, all right? So think of it like a chain, all right? Same principle. A chain has what links those little loops, right? So if this chain, if this loop pulls this guy over here, this one will pull it here, like that. Okay, so you're transmitting the force from one point to another. So same thing applies to a rope. All right, this is a rope. If you zoom in, it's like it has a dimension, right? But at any point, pick a point along the rope. This point. Now you can isolate. Remember what a free body diagram meant? It meant isolating a certain part. So if I consider this point here and isolate the left portion of the rope, okay? So it's like a free body diagram. So actually, to make it more realistic, let's extend this a little bit further. Okay, so this is a long string. Well, it could be a straight one as well. I just draw it in a curve. Doesn't matter. The point is still there. I'm just isolating one portion of the wire, the string, the rope, whatever I'm analyzing. And that's my free body diagram, right? So this is the object under interest. But these two portions, which are outside that blue line, are exerting forces. Like this one here, pushing it, pulling it to the right. And this one over here, pulling it this way, okay? So in most cases, these will be the same, T. All right, so, and it's going to be uniform. If you look at this point over here, okay, and then isolate the left and right hand sides, you will find the T. Depending on which part of the string you're isolating, all right? In our problems, you won't do this too much, but I'm just telling you why T is the same throughout the rope. And for that reason, actually, let me draw that box here and the rope attached to it. It's customary to use double arrows, okay? Whenever you see this symbol here, don't get confused. It means an arrow pointing this way and another arrow pointing that way. That has to do with this fact, okay? So it depends on which part you're analyzing. Like let's say you have two objects tied with a rope, and then there's a second rope here, and this rope is tied to the ceiling. Okay, this symbol is usually what I use for ceiling, all right? So there are two ropes there, and there's no reason why the tensions in those ropes should be equal. They're not equal. But within the rope that you're looking at, the tension, you know, could be pretty much the same, as long as it's not a heavy rope. If it's a really heavy rope, thick rope, the rope itself will have a weight, which you may not be able to ignore anymore, but for most problems, it's something negligible. So you would put two arrows here, and also here, and call it maybe T1 and T2, okay? So the arrows mean if you want to isolate one part of this setup, let's say I'm just isolating the mass in the top, and if I draw the free body diagram, I have to use T2 and T1. Okay, that's what it means. So if I want to isolate this guy here, then I just have T1. I don't care about T2. That's what isolation means, right? So please don't get confused if you see those double arrows. That's simply about this nature of tension force in the strings and ropes and chains and wires and strings, all right? Okay, so let's solve a problem, okay? Let's do something practical. Let's solve a problem and analyze what's happening there. Let me draw a picture first, a physical picture. It doesn't have to be an artistic picture, very simple, telling you what's going on. And then from that picture, move on to free body diagrams, okay? So let this be not just one object, a couple of objects together, tied together, okay? Let's say you have a birthday present, okay, a box. Let's do something fun, okay? Here's your box, birthday present. But somebody maybe, you know, wants to joke around or something, and you know those birthday balloons, a balloon with helium gas in it. So let's say someone ties a balloon. Let's say someone ties two of these balloons, okay? So from here, you have a balloon. That's a big one, all right? And then there's another one, even bigger. Okay, I don't know how to draw a balloon. Let's say something like this. I think it's good enough, okay? But these are tied like this. All right. Maybe they're strong enough to lift your little present there, okay? Who knows? Let's think about all the forces that are in play here, okay? Now let's start with the box itself. I'm going to use green. I said the box has a weight. Earth pulls it downward. Okay, we're going to talk about gravity in detail in a little bit, but for now, let's just call it W. Stands for the weight of the box, okay? Well, what about the balloons? The balloons have weight too. No matter how light they are, they still have weights. Okay, so why don't we also include them? Just gonna put an arrow here, another arrow there, because Earth pulls everything downward, okay? So, I can show all the forces that I can think of, but then focus on only some of them, alright? So, W, I've already used W. Why don't I call this one W left, L, and W right. It may not be the best notation, but it's okay, okay? Just to show that these are different, not necessarily the same. Okay, what else? Let's say there's no air in the room, so, I mean, there's no wind in the room. There has to be air, right? The air has to lift the balloons. Actually, speaking of that, let's also show the buoyancy here. Buoyant forces. Let's call it FL, how about that? And then this one, FR. This is nothing but the buoyant force. Air lifts the balloon, okay? The balloon is filled with helium gas, which is lighter than air. So they want to float. Just like when you put a piece of wood in water, it floats, right? Or if you start at the bottom of a pool, it goes up. Same thing happens to these balloons. They're filled with helium, so they want to go up. So these two blue arrows represent those two forces. These two balloons touch each other right here. And this is the point where they touch. Touch means contact, right? There must be a contact force. So the balloon on the left exerts a force on the balloon on the right. This way. F. Now let's use a different notation. The balloon on the left pushes the balloon on the right. Why don't I call it FLR? Okay, it's not confusing, right? There's two indices. FLR. FLR means the force the left balloon exerts on the one on the right. But similarly, the balloon on the right is touching the balloon on the left. It has to push it the other way. Okay, so that is what I'm going to call FRL. Alright? Now you got to be very careful here when you draw these forces. You have to pay extra attention. The reason is these two forces should be exactly opposite in direction. They don't have to be flat. There can be an angle to it, but you rotate both of them. All right? They have to be 180 degrees apart. That's actually a physics law. Okay, that's the Newton's law, Newton's third law. So it's a good place now to talk about Newton's laws. Newton's third law states that these forces in nature always come in pairs, and they are in the opposite direction, one to another, and they have equal lengths. The arrows have equal lengths, so the magnitudes are the same. So FRL is the same as FLR in magnitude, not in direction, but in magnitude. The word magnitude is reflected to this picture in terms of the length of the arrow. So equivalently, length of the arrow. Okay, so that is the are we recording, by the way? Let me double check really quick. Recording is in progress. Good. So the equality is about the magnitude, not the direction. Actually, if I have to be very precise, I'm gonna now place little arrows on top of each force, but I can't say they're equal anymore, because once I introduce these little arrows, I'm talking about the vectors themselves, not the magnitude or the length. Length plus the direction, okay? The direction is important. And whenever you have two vectors pointing in exactly opposite directions, one is the negative of the other. I'm going to put a negative sign either in front of FRL or FLR. Doesn't matter which one. They're identical, okay? I put a negative sign in one of them. Now I know that they're pointing in opposite directions, okay? So this is called Newton's third law, also called the action-reaction principle. Action-reaction principle. And these forces are called action-reaction pair. All right? There's something very important here, though. Usually I don't start with Newton's third law. I start with Newton's first and second laws. But just because this problem gives a good opportunity to talk about Newton's third law, I started with the third law. The important thing is, okay, these forces, in order to be an action-reaction pair, have to be acting on separate objects. Okay? I mean, it sounds trivial, but it's very important. It's a very common mistake to think about two forces that you can spot in a picture. They are indeed in opposite directions, and they are indeed of same length, which lets you to write this equation just like this, mathematically identical, but they do not form a Newtonian action-reaction pair for the reason that they act on the same object. Okay, we don't want that. Example, it's a remote. I'm just holding it like this, okay, with my hand. Now we're going to go back to the balloon problem, but let me just draw a picture here, because that's a misconception. Okay, I'm just going to draw a picture here. It's my hand, let's say. Okay, very bad picture, but it's my hand, like that. And there's the remote I'm holding in my hand. Okay, let me use a different color, at least. And it touches, okay. Something I'm holding in my hand, doesn't matter what it is, okay. Now just focus on the object, the green object. I'm holding it, which means I'm exerting a force on it, which means I need to put a F here, which is upward. Okay, sometimes I put an N here, Fn. N stands for normal, so normal force is what we call it, normal force. The word normal in physics and in math just means 90 degrees, nothing else, okay? 90 degrees is what we call normal. Surface normal, you may call it. By surface, I mean this surface right there, which is my hand, or the surface, the plane that is represented by my hand. If this force makes, 90 degrees with that surface, we call it a normal force, all right? That's simple as it. So when we're focusing on the object I'm holding, number one, it's the force that I'm exerting on it. The second force, number two, its own weight. right? Pulling it downward. And I don't really see any other forces acting on the object. Only two forces exerted on the object. You know, I end up with a result. Hey, these forces should be equal to each other, okay? Otherwise, I mean, imagine this was a gold bar, okay, and a small kid is trying to hold it. It would be too heavy, right? I mean, if the weight is greater than the force you can exert, you're gonna drop it, or your head will hit the table, all right? I mean, it's gonna move, it's gonna speed up, let's say, which would mean that weight would be much greater than the force you can exert, the maximum force you can exert or something. That's not the case, I'm just holding it. Okay, so I can safely say that Fn and W are the same. All right, so Fn is equal to the weight. All right, but if I want to write these as vectors, I have to now include that negative sign, right? For the same reason I explained 5 minutes ago, because they're pointing in opposite directions, right? These are vectors. So if I just look at this mathematical equation here, oh, I see it, okay? I have two forces. They are in opposite directions, and they are equal in length. Oh, I must have stumbled on an action-reaction pair. Here, this is Newton's third law. No, it's not. It's not, because both forces in this picture act on the same object. All right? Act on the same object. The rule is, for Newton's third law, the forces should be applying on different objects. So does it mean that, how is it a law then? I mean, if I don't see Newton's third law here, how is it a law to begin with? No, it is there. If you analyze it, actually, Newton's third law is still there, because what I drew here is not the whole picture. Now think about it. Earth pulls the object downward, okay? In return, according to Newton's third law, the object pulls Earth towards itself. So in order to have a complete picture, I have to show the Earth here. And for W, let me use the same color now. I have another force, maybe call it W prime. W prime is this green object pulling the green Earth in the opposite direction. Now W is equal to negative W prime. Now this is, yes, the third law. Okay? This is the third law. That's not the third law. What about Fn? Don't you think Fn is lonely, right? I mean, that force needs a pair, the other side of the pair, right? The other force. If Fn is the action, meaning I'm exerting a force on the object, well, there's a force that the object exerts on my hand. That's the reaction to Fn. So let me use green again. This is the force that I can maybe call Fn prime, and Fn is equal to negative Fn prime. I found another pair, action-reaction pair, right? Fn is my hand pushing the object, Fn prime, the object pushing my hand downward. So I found two pairs as examples of the action-reaction pairs in Newton's third law. But this one here, if you only consider Fn and W, the normal force and the weight, although mathematically you can write it like this, these two do not form a Newtonian pair. Okay, very important point. Okay, so let's close this parentheses here, and let's go back to our balloon example over here. I was just talking about FLR and FRL, which are the action-reaction pair, okay? Now, let's only focus on our object, your present, birthday present, okay? If you do that, which means you're isolating your object here. Isolate this. And draw a free body diagram for the object only. Isolate and draw a free body diagram, FBD, free body diagram. Okay? Let's draw it. Let's use that XY again. X, Y, these are the coordinates. Now this box here is just this object here at the origin, right? And I already have a force that is exerted on the object, which is the weight of the object. So let's include it. W. Okay. So another point, when you're drawing free body diagrams, please use a represent it in a way that gravity points downward. Okay. I mean, I see on some papers you rotate everything, or you don't rotate X, Y, but still show W, the weight, pointing in some other direction. Okay, don't do that. It's confusing. Okay, don't do that. It's weight. It just points downward. Are we done with the free body diagram? No, because there are still forces here which we haven't talked about it in this picture, but we talked about before. It's a tension force, right? So let's use red again. The tension forces. Remember those double arrows? Yeah, here they are. But when I'm transferring them to the free body diagram, I only use the ones that are within those dashes. Okay, so I will have here, this is the tension in the string on the right, call it TR, and there's also a TL, remember? And now I have here a TL, so TL and TR. All right, now it looks complete. Well, if the system is accelerating upward or downward, I have to also show that in the free body diagram. For now, let's not talk about that. Let's ignore that, okay? Let's say it's not accelerating, no acceleration. It just stands, it's just suspended in air like this. Okay, no acceleration. Well, no acceleration does not necessarily mean no motion. I'm going to talk about Newton's first law in a minute, but it doesn't change anything. Let's say no acceleration and no motion at all. All right, everything is in equilibrium. No movement. It could be, right? No movement. So we have equilibrium. What do I do with this graph then? Why? I have to also include some angles here, like maybe theta 1 and theta 2 here. Okay. Now remember when I was telling you about the object I'm holding, okay, if I'm just holding like this, this means the force I'm exerting on the object, the normal force, is equal to the weight of the object in magnitude. Using same kind of reasoning, all right, I can use this free body diagram to come up with equations that involve these three forces, TL, TR, and W. All right. But the good thing is I can do it in terms of the components of these vectors by using the Cartesian coordinate system. How? Like this. In the x direction. Okay, in the x direction, what's happening? Meaning if I decompose the two vectors here into their x and y components, what will I obtain in the x direction? And W does not even have an x component. Okay, again, if you're lost here, please watch the vectors video part 2. All right. So W, weight, does not have any x component because it lies in the negative y direction. But TR and TL, they do have components in the x direction. All right. Namely, TR has a positive x component, TL has a negative x component. So if I'm considering the sum, let's say, consider the vector sum of all of these forces. Namely, TL, put an arrow on top of it, plus TR, put an arrow on top of it, plus W, weight of the object. If I write them like this, I'm talking about the vector sum, okay? I'm adding all of them. What is this, okay? That will determine whether it's in motion or in equilibrium or if it's accelerating. Since I already gave you the information, there is no acceleration here, there is no movement, there is no equilibrium. This means that these forces are balanced. These are balanced. Which means the sum should be equal to 0. All right? Now, when we do Newton's second law, this will make very good sense. But even now, it shouldn't be too hard to grasp, right? I mean, when you were holding the object, the forces were in balance. In that case, there were two forces, one up, one down. We just added one more force into the picture, pretty much. So we have a summation which has 3 vectors. They're added and give us 0. That's what equilibrium means, okay? So when you do that, you're actually saying the net force is 0. That's another way of saying it. The net force is 0. So by definition, the net force is nothing but the vector sum of all forces that are present. All right? If the net force is 0, you may have an equilibrium, all right? So if the net force is 0, this means its x component is also 0. Its y component is also 0. So if I want to write the x component of the net force, let's call it F net here, F net, which is equal to TL plus TR plus W equal to 0, that means that F net has an x component that is 0. Similarly, F net has a 0 y component. All right? So please do not confuse with this notation here. Maybe I should just erase this. I think it's obvious what I did here, right? I just wrote the x and y components. But what are those components? If you recall the component method of adding and subtracting vectors, what I really mean here is this. The x component of TL plus x component of TR plus x component of W, which doesn't exist, is equal to 0. So I can write TLX plus TRX plus WX. These commas are not necessary between L and X, R and X. I'm just putting them of habit, okay? You don't have to put it there. Same thing applies to Y. TLY plus TRY plus WY have to be equal to 0, all right? If a vector is 0, it means its component is also 0. So, I have my equations here. Let's write them clearly. Let's let's simplify them, all right? First of all, Wx, this is 0, okay? You don't have to worry about Wx because W only has a y component. You can simply call it W, drop the y in the x, okay? Now what about TLX and TLY, all right? So you draw a square or a rectangle, you box it, and then you do the same for TR, you box it, and find the horizontal and vertical sides of those boxes. Those are the x and y components. Okay, basic use of trigonometry here, starting with TL on the left. See, if this angle is here theta 2, all right, what is the sine of that angle? Sine theta 2. Sine is by definition opposite side divided by hypotenuse in a right triangle. Here's your right triangle, right angle. Theta 2, opposite side is this side. If you divide it by the hypotenuse, which is nothing but the length of TL, you will get the sine, right? Opposite divided by hypotenuse. What we're interested in for the x component is that opposite side, because I carry it down here. It's also this length here, right? This. But it's pointing to the left. The x component is in the negative direction. So if I rewrite this equation, I start with 0, and then I have here TLX. It's going to be a negative number. How do I solve for that opposite side? I multiply sine theta 2 by hypotenuse. Okay? Hypotenuse is the length of TL. So TL times sine theta 2. Then move on to TRX. This guy right there, TRX. It's a positive number. I have to use trigonometry again, but theta 1 is here, okay? I specifically chose this angle to represent the direction of TR. Why don't you consider the cosine of that angle? Cosine is by definition adjacent over hypotenuse, right? So in order to solve for adjacent, which is the one you're looking for, you multiply hypotenuse by cosine theta 1. So the x component of TR is nothing but TR times cosine theta 1. So do this for the y equation. 0 equals, now both TR and TL have positive y components. So using the same logic, TL cosine theta 2, this time cosine because I'm after this line here, this component, plus, and a positive, TR sine theta 1. This side is equal to that side in a rectangle, so TR sine theta 1. And then one more. What is that? W. Is it W or is it negative W? It's pointing downward, right? Negative W. Those are my equations. Okay. Step 2 finished. Step 1 was free body diagram. Now I have my equations. Now the rest is just math. Step 3 is solving these equations. Since I didn't start with any numbers, there is not much to solve here. You know, I'm just going to leave it there. But if I had numbers here, if I had told you what the angles were, hey, what is theta 2 is 25 degrees, theta 1 is 30 degrees, and the weight is 5 what? 5 newtons is the unit. Example, weight could be 5 newtons. This N stands for newtons. That's the unit. That is the unit for force. Now I talked about basic units last time. They were meters and seconds, right? These are for standard units. I didn't talk about the origin of those unit systems. It's in the book, you can find out, but pretty much historically A second has to do with how we measure time. Okay, in the old days, a day was just from noon to noon, and then dividing that would be enough. And then they realized that as the Earth goes around the sun, the time of the day changes from month to month. And then there were other complications. The Earth doesn't move at a constant speed around the sun, etc. So we ended up using nuclear physics again, okay? Because reactions inside an atom doesn't care about the Earth's location in space, all right? So we have a very good way of determining what a second is. I'm not going to go into detail. I can, if you're curious, just let me know. Same thing applies to meters, okay? And also we have kilograms. Kilograms, that's the unit for mass. All right, I haven't talked about definition of mass, which I will in a little bit. Mass is different from weight, okay? Mass is measured in kilograms, and the kilogram we use is roughly 2 pounds, and that is just based on a specimen, let's say a cylinder, which is kept in a museum in France. But there are modern definitions for that as well, because over time those objects, cylinders, they deteriorate, so you want something stable. So we can use modern physics again to come up with a good definition of what a kilogram is. Kilo means 1,000, right? So it's 1,000 grams. Maybe you're more familiar with grams, when you take medicine, those pills are in milligrams, for instance. Take Advil, okay, 10 milligram or something. So 1,000 grams is 1 kilogram. So kilograms, meters, and seconds, these are fundamental units. There are a couple of more like these. I think the total number is around 10. These are called fundamental units. And then there are units such as newtons, which is the unit of force. These are derived units. Now, without explaining why, I'm going to tell you what 1 newton is equal to in terms of kilograms, meters, and seconds. So 1 newton is equal to 1 kilogram meters per square second, okay? Now, once we do Newton's second law, this will make sense. But for now, just keep in mind that 1 newton is equal to 1 kilogram meter per second square. So, if the weight is 5 newtons, if I give you theta 2 is 25, theta 1 is 30, and weight is 5, what is left to do? You're going to solve for TL and TR. 2 unknowns, 2 independent equations. Good, okay? Use your algebra skills to solve for TL and TR, and you would be done with that problem. Going back to the picture that I drew in the beginning, okay? See, there are things that are here which I did not even use in the formula. In the solution. The buoyant force, the airlift, okay? The forces that the balloons exert on each other, the weight of the balloons. Those things have nothing to do with what's going on at the object, okay? Specifically, I focused on those 2 strings and the point they are tied to the object. That was my focus, okay? It's always the case in physics. You only focus on one part and think about it. If you're done with it, you can move on to other things, okay? You never try to solve everything all together. It's gonna mess things up real bad, okay? If you write down an equation which has FL over here and then W also in it, okay? Well, you may be on the right track if you're thinking the whole thing as a system, maybe, yeah, it may make sense, but it's rarely the case, okay? So you have to take it into different parts and analyze them separately. Okay, so I was just talking about mass. So what is mass? All right, what is mass? This kilogram. Now, there are basically 2 ways to define mass. And the 2 definitions end up being equal according to our modern. Modern means the last 100 years or so, I mean more actually, last 120 years. the two definitions are equivalent to each other. Number one has to do with motion. Okay, so let's open up a subtopic here, topic of mass and how it is different from weight, which we already discussed. Weight is a force measured with newtons. Mass is not force, it's measured in kilograms. Okay, that's obviously two things separate, physically different dimensional things, right? So what is mass? There are two ways of defining mass, I said. One is using concepts of motion. That's where Newton's first law is used, or that's what Newton's first law explains, right? Very closely related. And the second is also by Newton, but it's not one of the three laws. It's also due to Newton. What else Newton has discovered? Gravity, right? So you can define mass using gravity or gravitational concepts. Because in order for two objects to attract each other with this interaction, they have to have mass, right? It's like a chicken-egg problem, okay? Is gravity because of mass? Yes, it is. How do we define mass? Because there's gravity, okay? It's like a funny thing there, but that's how it is. It's very simple, actually. Let me start with number two then, since I mentioned already. Isaac Newton says that if there are two objects, object A and object B, and they're separated by a distance here, and usually, approximately we can use the distance between the centers of the objects. It's not exactly right, but for our purposes, especially if these are symmetrical, perfect spheres, it will be actually correct. Let's call it R. Is the distance between the two, okay? The distance between the two objects. The objects actually could be touching each other. Still, there's some R, right? I mean, R is not zero when they touch each other, because we're not measuring the distance between the surfaces of the objects. That would be zero. We're measuring the distance between the center, or better, we call it center of mass, all right? But in general, think about Earth and the Moon, okay? There's a distance between them, 384,000 kilometers, right? There's R. So the force between them, on A, it's to the right. On B, it's to the left. Now, Newton says these two forces are equal to each other. Equal. No matter how different A and B are, okay? They have to be equal. That's Newton's third law, remember? Forces never are alone. They have pairs, action-reaction pairs. They have to be pointing in opposite directions, and they have to be equal in magnitude. So how can we come up with an expression for F, a mathematical expression? And in that expression, if I change A to B and B to A, the forces are not going to change. Okay, how can I do that? That's how you involve the mass of the two objects, MA and MB. Let these represent the mass. Okay, mass is about pretty much how much material you have contained in that volume. Okay, that's a really rough description of mass, But in this sense, in the context of gravity, the number that represents the mass has a specific role. I take them, MA and MB, I multiply them. Okay, I multiply them. Now, multiplication is important because if I change the order, the multiplication doesn't change. MA times MB is equal to MB times MA. Everybody knows that, right? I mean, it's just simple. I'm not saying in physics it's always the case. There will be cases which you will never see in this class when A times B is not equal to B times A, okay? There's serious physics there, but not our physics. MA. So a multiplication is necessary because we want interchangeability between A and B. And you may say, okay, instead of multiplying, why don't you add them? Because A plus B is also equal to B plus A. Yes, it is, but it doesn't work in this case, okay? It doesn't work. Why it doesn't work? Because the force is proportional to the mass. Greater the mass, greater the strength of the force. Okay, remember, I can't feel the force if it's small objects, but if one of them is the Earth, now I can feel the weight, right? So size and mass does matter. There has to be a proportionality. Remember, proportionals from the video on. So this force here has to be proportional to both MA and MB. If I add them, I will lose that. So I have to multiply them. Okay? Furthermore, I know that if these objects are close to each other, the force is great. I mean, Earth pulls the moon, but if the moon was 10 times farther, maybe the moon was going to fly away, right? Who knows? So the force dissipates, the force decays, the force gets weaker as the distance increases. All right? And how can you achieve that? Using math. All right? Like you can't multiply this by r. That would involve a linear relationship. All right? No, we want this to decrease with r. So you can divide it. That's a good way, right? You can divide this by r. If you divide it by r, it does decrease as you move away from the other object, but experiments tell you a slightly different story, okay? It's going to be an r squared instead of r. Let me put it that way without talking too much about it. It's not r, it's not r cubed, it's not r to the power 2.5, it's r to the power 2. Experiments. Now, which experiment? In the 18th century, a very famous experiment done by Cavendish. Cavendish wanted to find the mass of the Earth, or the mass density of the Earth. It was an important number in geology at the time. Okay, so we're talking about 1700s, 18th century, let's say. He devised an experiment where he used a torsion balance. Torsion balance. He took a piece of rod and then tied a wire into the middle, okay, and the other end maybe in the ceiling or something. So here's the rod, here's the wire attached to the ceiling. Now it's not only balanced this way, but it's also balanced that way, because when you twist a wire, there will be a restoring force inside the wire. It acts like a spring. And you might have seen some old clocks which work like that, you know. They're in the glass, and then there are four, depending on the model, you know, rotating like this. So you put balls here, and it's free to rotate, okay? So it can rotate on a plane. Not like this, but like that, okay? It's free to rotate, but if you move it from the equilibrium position, it wants to go back to the original. It acts like a spring in a way, but that's why it's called torsion balance. That kind of force is obtained by twisting the wire. That's why we call it torsion. What does this have to do with gravity? Well, he did this now. Really smart. He took, these are, let's say, made of lead, okay, really heavy thing. Heavy. And then he took even larger lead balls, and he placed them on the same plane, just a little bit apart, okay? Maybe here. He may attach it on the wall, okay? Then he put one here on the wall, attach it to the wall. But what happens is two objects will attract each other. Okay, and I'm talking about the one that is really close to other. So I don't worry about this lead ball on the left attracting the other small ball on the right side. It does, but that effect is maybe negligible. I'm basically interested in the force between these two and then those two. Now, I said that force is so weak, but with a good torsion balance, and they had good mechanical engineers back there, watchmakers, okay, and they were good equipment, you can actually measure this force. You can measure it, or better to say, you can find how that force compares to the actual weight of the ball. Because they knew that the weight is because of the Earth's pull it, okay? So you have a ratio of forces, let's say. And from that, since you know what the weight of the ball is, you can come up with mass of the Earth, right? So let me name these M1, M2, M3, and M4. Since you know all these numbers, and now you know what the force is, F here, and also F there. Let's say they're symmetrical, same force, F. Since you know that all these four masses are also pulled downward by Earth, and in that sense, going back to this expression here, MA and MB will be Earth and the lead ball that you have, okay? What is the unknown? Well, the weight, the mass of the Earth is unknown, okay? So he did this experiment to determine the mass of the Earth, and today we interpret it a little bit differently. How we write this proportionality in a form with the equal sign here. Instead of proportional, we are equal. So there's still MA and MB and R squared here. But in order to make this an equality, we have to introduce a constant here. G is called the gravitational constant. Okay? Remember, it's weak. The force here is so weak. The gravitational constant is a small number, 6.67 times 10 to the negative 11. Okay, 10 to the negative 11. 1 over 1, 10 zeros next to it. So such a small number. It's not dimensionless. It does have a unit. So let's find the unit. I said force is measured in newtons. Mass is measured in kilograms. So kilograms times kilograms. We have kilogram squared. And we have here, what? R. R is measured in meters. So this is meter squared. So G here, the gravitational constant, should have a unit when multiplied by kilogram squared per meter squared, should give me newtons. Okay, so I can write it as Newton times meter squared divided by kilogram squared. So that when multiplied by kilogram squared over meter squared, those meter squareds and kilogram squareds will cancel. Only newtons will be left, which will be the unit of the left-hand side. Okay, so you can either see this one in the books, or remember 1 Newton was equal to 1 kilogram meters per second square. Remember, kilogram meters per second square. You can plug this in here, so you can also write it as kilogram meters per second squared times meters squared divided by kilogram squared. So meters times meters squared gives you meter cubed. Okay, and then kilograms divided by kilogram squared, you have kilogram and then second squared. If I didn't mess it up, there's an alternative way of describing the unit. Okay, either use Newton meter squared per kilogram squared or this. All right, so that's Newtonian gravity. And in Newtonian gravity, you need mass. So that's one way of describing mass, right? See, I mean, everything is static here. There's no motion, really. This was the second way of talking about mass. A different aspect has to do with objects in motion, okay, which will be explained by Newton's first law. Now, what is the first law is about, and what is motion to begin with, all right? Well, we know what motion is. I mean, objects have coordinates. If everything in this room is where they are, those coordinates do not change. But once x, y, or z changes in time, right, we're talking about motion. So motion has two components, x and t. X has to change in t. So x, if x is position, x has to change in time, changes in time, which is t, right? You can either use a graphical representation and say, hey, this axis represents time, this axis represents where my car is on my street, and the origin is my house, that's 0, okay? I start driving from my driveway all the way to the end of the street, you know, so the position of my car changed along the x direction. In time, I ended up being here, okay? You can either show it graphically or mathematically, and you guys should be familiar with this idea. You could use functions, function of time. So if x is a function of time, you can write it like this. Okay, so the t in parentheses here does not mean you're multiplying t by x. It just means that x is a function of t. You call it x of t if you like. X of t. Okay, it's a function. And you know, functions have to obey some rules, like you can't have this. Okay, why? Because it means you're going back in time. It means you're at two different places at one time, which are physical impossibilities. That's as far as the physics we are going to learn. Okay, so it has to obey some mathematical principles. It may have a maximum or minimum. You know, I mean, I'm sure you're familiar with this. You don't have to have you don't have to know calculus to know what I'm talking about, right? So whenever we speak about motion, we're talking about actually a coordinate, x or y or z, doesn't matter, changing in time, all right? Now, this change in time, how are we going to relate this to mass? That's the question, right? That's what we're after. Is this change in time an absolute change? Or is it relative? Remember, in the example, I said, let x represent the position of your car on the street. Initially you were at home or your driveway, and now you're at the end of the street. You know, after 10 seconds you're here. But with respect to what? With respect to the road, right? With respect to the street, you're in motion. What if there were two cars on the street, a two-lane road, and the car is moving right next to you on a two-lane road, with a 2-lane this way and 2 lanes that way, let's say 4-lane road, and the car has the same speed, okay? I mean, you can roll down your window and she can do the same thing. You can shake hands, okay? It feels like they're not moving. Yeah, they're not moving in your frame. They're moving in the other frame, which is the car, which is the road or your house. And you both are moving in that frame. But if you change the frame of reference, you're not moving, okay? So are we moving or not? Well, we don't know, okay? I mean, is Earth moving? Yes, in the solar system. Well, I don't feel anything right now, right? I mean, I don't feel like I'm moving. Same idea, you're out there in space, outer space. There's nothing next to you. I mean, you're not near a planet or space station, okay? And somebody turns off the engines in your spaceship, Rocinante from Expanse, right? You turn everything off, absolute silence. Are we moving or not? How would you know, okay? Maybe you are. It depends on what reference frame you're using. If your reference frame is the other starship next to you, you're not moving. But maybe both of you are moving near speed of light with respect to Earth. Okay? So, motion is relative. And you cannot feel the motion. There are infinitely many reference frames. This means right now I have infinitely many speeds. You can measure it with respect to the sun. You can measure it with respect to the center of the galaxy. You can measure it with respect to the car in the street. On and on. Okay, you may have infinitely many speeds or velocities. If you think about a direction, you're thinking about velocity. All right. Speed and velocity are not the same thing. Velocity is a vector, speed is a scalar. A scalar with a direction is what a vector is, and the velocity is actually a better term to use here because the direction will matter. I don't know what my velocity is because I don't know what reference I'm using. I can only talk about reference frames. Okay, so you can't feel motion. What can you feel then? The only thing you can feel is the change in motion. Let's write it down. You can only feel changes in motion. The way you move has changed. How has it changed when you drive? You hit the brakes. There's red light. You have to slow down. So slowing down is something you can feel. In the passenger seat, maybe they will be feeling it, right? They feel like, hey, someone pushing me forward. You know, maybe they were reading something. Oh, what happened? Oh, we stopped. Okay. Or you're speeding up. You know, if you're driving a Ferrari, and when you hit the gas, and then you're pushed back into your seat, you feel the change, right? Or going back to the example of outer space. Let's say you are in a spaceship, but you're just in a room, okay? Room. And you're far from Earth. There's no weight, right? You're not pulled to any side of the room with gravity. So you don't know which side is up, which side is down. Maybe there's an electric lamp there. That's when you can tell, right? But other than that, there's no up and down in space, right? But what if suddenly somebody powers up the engines of the spaceship and the spaceship starts moving in a direction, but not just moving, but speeding up, okay? Fired rockets, whatever propulsion system you're using. Now you're increasing your speed. You have to increase your speed because once you start exerting a force, that's what brings us to Newton's laws. There will be a change in the motion. If that's the case, you will be pushed to one side of the room, just like you were pushed to your chair when you were speeding up in your Ferrari. Same thing will happen in the spaceship, and you will be pushed in one direction, or you feel like you're pushed, okay? And then you will tell, hey, okay, I know where the engine is, where the nose of the spaceship is, and etc. All right? So you can only feel the change, all right? So, change in motion means change in velocity. Change in V, okay? V with an arrow, that stands for velocity. Not just speed, but direction. And you may have cases where the speed is not changing, but your direction is changing. Why? If you're on I-10, okay, I-10, and then this is 290 here, I-10 and 290, or 610, doesn't matter, I mean, different highway. You make a turn, okay? It's a nice smooth turn, there's not much traffic. So your speedometer on your car says 45 miles per hour. Your speed is not changing, but you know your direction is changing. You were going east, now you're going south, right? So your velocity is changing. If your velocity is changing, that is considered a change. So the change in the speed, it doesn't help us, because here it's not even changing. The speed is not changing, but the velocity that is changing. Now, if the speed is also changing, yeah, well, okay. I mean, if you're going straight and your speed is changing, yeah, that definitely counts as a velocity change. But I'm just saying there are cases where speed doesn't change, but velocity changes, right? So these all create a fictitious force on you. You feel yourself pushed in a direction, okay? In reality, nothing is pushing you, okay? What happens is your body, your mass, that's why I brought it up, your body wants to go in the same direction it was going before you turn the wheel, okay? This is what we call inertia. Inertia means objects do not like changes in motion. They want to stay the way they were. If it was going in that direction with half of the speed of light or 1 meters per day, doesn't matter, it wants to stay that way. But if there is any change in the velocity because of an external force, this could be the force of a space rocket, or it could be the force due to the friction force between the wheels of your car and the road. It could be anything, okay? That creates a change in the velocity. Therefore, your body has to comply. That's when you feel like there's a force acting on you, all right? So if you make a right turn, you feel like you're pushed to the left side of the car, but actually it's the left side of the car is pushing you to the right when you're making right turn. And vice versa when you're making a left. When you're making a left turn, you feel like the guy in the passenger seat feels like they're pushed to the right, but that interaction is actually on their right shoulder is the right door pushing them to the left, right? So something has to push them, either the seat or the door, otherwise they would fly from the window, right? I mean, that cannot happen. So something has to exert the force in order for the mass to comply with the change in the motion. That's about inertia. So this is a way of describing mass through inertia, and we will see it later, but let me just give you what it is from now. It doesn't hurt. There's an equation that looks like this: F equals ma, where F is the net force and a is your acceleration vector. We will define what acceleration means mathematically. That's pretty much the change in velocity, but we're going to do it in detail, okay? I'm just telling you now what we'll see later. But you can interpret m here as a definition of mass through an acceleration, right? So that's another way of doing it. So we covered law of gravity here. Okay, I can give you a homework. Find the force of gravity between Earth and the Sun. The distance between Earth and the Sun is 149 million kilometers. Mass of the Sun is 2 times 10 to the 30th kilograms, and mass of Earth is 5.97 times 10 to the 24th kilograms. So use these three numbers and g here and find what F is, okay? This F will be the force Sun exerts on the Earth, which is equal to the force Earth exerts on the Sun. Newton's third principle. You can find it and see what kind of a number we're talking about. If you're really enthusiastic, you can calculate the net force on the moon during a solar eclipse. Here's the Sun, here's the moon, and here's the Earth, right? The moon comes in front of the Sun. That's when the solar eclipse occurs. This means that Earth is pulling moon to the right and the Sun is pulling the moon to the left. You can look up these numbers, meaning moon's mass and the distance between Earth and the Moon, I think I told you 384,000 kilometers. What will be the net force on the Moon? Because one is pulling that way, the other one is pulling that way. You subtract this from that, you find the net force, okay? These are really fun exercises, and they're not very simple if you're not used to deal with numbers with exponents, and you can easily make mistakes. I suggest try it, okay? Find the force between Earth and the Sun, and then find the net force on the Moon during a solar eclipse. What about the lunar eclipse? When the Moon is on the other side, when the Moon is here, then both Earth and the Sun pulls the Moon to the left. Then you have to add those, okay? Think about that. All right, so mass is defined like this. What is weight then? What is weight? Weight is not the same as mass. These are not equal. All right? Maybe in daily language, you don't, especially if you live outside the United States, you know, you go to groceries and they say, hey, give me 2 kilograms of apples, okay? Well, 2 kilograms is mass, but nobody says, okay, I need 20 newtons of apples, right? So, but when you say weight, you're talking about the force, all right? So there's an expression for weight in terms of mass, though. M times little g, not the capital G, but the little g. This g at a specific value, it's more or less equal to 9.8 meters per second square. The unit has to be meters per second square, because when you multiply it by the mass of the unit of mass, which is kilograms, you have to get newtons, remember? So this has to be in meters per second square. Well, this number changes. It depends on where you are on Earth, really. I mean, are you at the sea level, or are you at the top of a mountain? Or if you're at the sea level, are you in Gulf of Mexico, or are you close to the North Pole? Because it changes, okay? The value of g changes. This is called acceleration due to gravity, or gravitational acceleration. Okay, that's what g means. You multiply it by m, this will give you the weight of the object. So the weight changes, mass doesn't change. You take a bar of gold, it has the same mass on Earth, same mass on the Moon. But its weight on the Moon will be 1/6 of its weight on Earth. You take it to Rocinante, the spaceship, its weight is 0, but it's still the same mass, okay? So mass never changes, but the weight depends on g. The g on the Moon is 1/6 of the g on Earth, for instance. G Moon is 1/6 of g, our g. Our g even changes, depends on where you are, okay? You may have a plane, you have equipment on the plane may fly over Gulf of Mexico just to detect the changes in g, because it's going to give you clues about what's under the ocean bottom, okay? Do you have rocks, or do you have salt? You know, the density will be different. All that sorts of stuff, okay? So the variations of g. You can even find out your location on Earth using the variations of g, because Earth is not perfectly a sphere. It's actually larger at the equator. There's a bulge, okay? So this means when you go from the country Ecuador all the way to North Pole, you're actually getting closer to the center of the Earth. Right? Sounds funny, but that's the truth, okay? So you expect g to change, right? So can I find g, little g, in terms of capital G? They must be related. Oh, the capital G never changes, okay? The capital changes, g, 6.67 times 10 to negative 11. That's a universal constant. It's the same everywhere in the universe, but little g obviously changes from this point to that point. So how are they related, if you're curious? You can do a little experiment here. Let's draw a stick figure. Let's say this is me standing up in Houston, okay, on a bathroom scale, okay? I'm just reading the number I see, okay? That's my weight. Actually, I'm reading the normal force, right? Anyways, at that point, I know that Earth pulls me towards itself this way. That's what I call the weight, all right? This is the weight. Now, this weight is my mass times this little g. I know that now also. Great. But an hour ago, I was telling you about how the capital G is used, the definition of mass through gravity. So I can also write this as capital G times my mass times Earth's mass, 5.97 times 10 to the 24 kilograms, divided by the distance between me and the center of the Earth, squared. Now, if I want to be exact, I should say the distance between the center of the Earth and center of me, some point near my belly, okay? But if you think about it, from my belly to my feet, it's less than 1 meter. 1 meter is nothing compared to what is R? R is 6,371 kilometers. That's negligible, okay? So it doesn't hurt to use this value, the radius of the Earth, for R, which is normally the distance between the center of the mass of two objects. So, if I do the math, something nice happens. That's the cancellation of M here. My mass doesn't matter, which is great, right? So G can be written as capital G. Let's plug in the number now. 6.67 times 10 to the negative 11. I'm not writing the unit to save time and space. Times Earth's mass, 5.97 times 10 to the 24th power, divided by 6,371 kilometers. So I need to add or multiply it by 10 to the power 3, because 1 kilometer is 1,000 meters, and I need to square that. So let's do the math here. Okay, take your calculator, Casio FX991EX. I know how to use this one. If you have a Texas Instruments, learn how to punch in exponential the numbers with exponents, right? So 6.67, 10 to the negative 11 times 5.97. I hope I remember the numbers correctly. 24 divided by 6,371, 10 to the third squared. Great. 9.81. 9.81036. Okay, I mean, you don't need to include all the digits, all right? You can cut it somewhere. 9.81 is enough meters per second square, which was this value I told you earlier. Okay, that's how you find G on Earth. If you want to find the G on Mars, you just replace M for Mars mass and R for the radius of Mars. And the number you'll find is about a third, okay? So on the moon it's 1/6. On Mars, G on Mars is 1/3 of what G is on Earth. So divide 9.3 roughly by 3. I think that's what I remember. Okay, so on Venus it could be close to Earth, I guess. In outer space, if there's nothing around, there's no G, okay? Theoretically, you can make G a function of your distance from Earth, but it becomes pointless. I mean, hey, what's the value of G, a third of the distance between Earth and the moon, okay? I mean, yeah, it's a problem, and you can get a number for it, and maybe book has even made problems like this, but I don't find it practical. Let's just use G where we're not really far from Earth, okay? Later we're gonna solve for projectile problems. Okay, you kick a football, it flies and then comes back. Okay, in that area where you play football, you can even assume Earth is flat, no problem. Okay, so you can use equations where the little g does not change. But if you're firing intercontinental ballistic missiles from one continent to another, okay, well, it's not a football problem anymore. Then you have to use capital G, all right? And we're not going to go there, but I'm just letting you know it's going to be a different story, because it's going to be a lot of separation from Earth. It's like a spaceship, right? It's a ballistic missile, but still it has to go far, very high altitudes. And then it doesn't make any sense to work with little g because it changes, all right? You work with capital G. And you think in terms of elliptic orbits, you know, it's just like a planetary problem, pretty much, you know. All right, so that's what weight is about. So weight is not mass. Speed is not velocity, okay? Please do not mix those. The final topic I want to talk about today, before I let you guys go, is friction. We haven't talked about friction yet. Friction. Why does friction happen? Why are some surfaces better than others with less resistance? So here's an object A touching an object B. I mean, they look like flat and nice. You can sand an object. You can sand with 200 grit and then 600 and 1000. Every time you go to higher grit, means those sandpaper has the sanding material becomes denser as the number goes up, and you can have a smoother and smoother surface until it becomes like glass, right? And then you slide. Yeah, you can do it, but no matter how much you do, there will always be some irregularities, which you can see if you look with a microscope. So let's put a microscope here. Let's focus on this area with a microscope. So this is the picture, the real picture. What looked like a smooth surface here suddenly becomes like this. Rough. I'm just making up a shape, okay? But remember, there's another one, which is B. So this was A here. B is also like that. So it touches A in points. Okay. So when they touch each other, when A touches B and vice versa, there are forces there, contact forces. Remember contact forces? So B pushes A this way. In return, A pushes B that way here. Here, maybe B pushes A up, and in return, A pushes B down. Here, B pushes A to the left, and A pushes B down, so on and so forth. So Newton's third law, action-reaction pairs, happen there. Okay? And there are millions of these forces, because there are a million different contact points. Not only this direction, but there's also the other direction. I mean, there are billions of these contact points. Just imagine a supercomputer could measure and do the vector math here, vector calculation, okay, addition pretty much. What would it find? I can tell you right away what it would find, okay? Means like, take this one example, this one, and then that one, the one on the right, okay? All you have to do is to draw your x, y, and then find the components. This is the oops, what color is that? Let's use white. The boxing method, right? You draw a box around, a rectangular box around this one, right? That one, and you find the two component vectors and see what the net force is. All right. If you do that, if you know for a fact that let's say there is no net force in the x direction, okay, you could just find these components and add them up to give 0, you know. Or if there is a net force, sometimes there is a net force. I mean, maybe a child is pushing a big refrigerator and the refrigerator is not moving. This means that there is a friction force that stops the refrigerator from moving, and that has to be in the opposite direction. The kid exerts his force. Okay, so no motion does not always mean no net force. I'm sorry, no friction. You know, there could be friction, but the net force could still be 0, right? Similarly, in the y direction, we know these components here, this component, and every other force which have a y component, they will add up to give me the normal force that I was telling you earlier, Fn. Fn is nothing but the surface B exerting the force, the net force B exerts on A in that direction. Okay. So the net force B exerts on A in this direction is normal force. In the horizontal direction, if there is one, it could be the friction force. That's what we're after anyways. So that's the zoomed in picture with a microscope. Since we're not going to do this kind of supercomputing task, what we do is only represent that net force by a friction. So here's the box that your little brother is trying to push, but it's not moving yet. Okay, so here's the force that he exerts, F external, and then there's a friction that resists it. This is F, which stands for friction. Okay, but he's determined. He wants to move the thing. Okay, so he pushes it harder and harder and harder, and there will be a point where it can't hold anymore. It'll be on the verge of moving, and it's going to start moving. Okay, and you might have felt it before. A heavy object, you push it hard and harder, and once it starts moving, it feels like you don't have to push it that hard anymore. I mean, you may still push it in order to move it, but not that hard anymore. Okay, that's because there are two types of friction: static and kinetic. Now, if there is no motion, this is the static friction force, still there, and once you move the object, it becomes the kinetic friction force. So let me try to explain what I just explained in the graph format. Okay, so let the horizontal axis be the force you exert. You start with 0, you barely touch the object, and you start pushing it harder and harder, which means you're moving to the right on the graph. But then there's the little f, the friction force, that opposes you. All right. Now, if you are in the static phase, which I'm going to write here on the left, if you're in the static phase, no matter how hard you push, the object will not move, which means F external is equal to little f in magnitude. Not in direction. Direction is opposite, but in magnitude. I'm not talking about the third law. I'm only talking about the net force being equal to 0, right? So, no matter what you do, no matter how hard you push, it's not moving. That's because as you increase F external, this internal mechanism, which you can see using a microscope, adjusts itself, so the friction force also increases exactly the same amount. So you can draw a 45-degree line here. As long as you're in the static phase, this friction force will be equal to the force you exert on the object. All right? Until it can't hold anymore. And then there's a sudden tiny relief, and then you start moving. And turns out that once it starts moving, you may push harder and harder if you can do it, but it will not make it will not the friction force greater. Let's put it that way. So this means the friction force will remain around here. Okay, so there's a drop here. There's a drop. It's going to drop like this, and this will be the kinetic phase now. Kinetic phase. This is where you change phases from static to kinetic phase, okay? So once the object is moving, the friction force is still there. It's not zero. It's not zero, it's present, but it is less than the maximum static friction force you experienced just a moment ago, which was here. This is F static maximum, and this is F kinetic, Fk. But as you can see, Fk is always less than Fs maximum. All right. So that's very important to remember. What else can we tell about this? Now, as you can imagine, I mean, if it's a light box, friction is not that hard, it's not big. But if it's a refrigerator, you have a lot of friction. If you have anti-skid plastic or something like this under your furniture, maybe it's even difficult, more to move. So it depends on two things: the material these are made of, both the object and the floor. Okay, are we talking about wood against wood, or steel against glass, or steel on ice, or rubber against wood? Okay, or wood on, endless possibilities. So it's an experimental science. Okay, we have to do the experiment in a lab in a controlled environment and write down the numbers. And also it depends on how heavy the object is, or more precisely, it depends on the normal force that is present here. Normal force, Fn. Okay, so it turns out that this Fs maximum is equal to the normal force. Both Fs and Fn are measured in newtons, so dimensionally they are equal, but you need a factor, okay, a coefficient we call it. The letter mu is that coefficient, so we call it the coefficient of static friction. In a similar fashion, you can define Fk as mu k times Fn, and obviously mu k has to be a number less than mu s. Okay, so you can look up those possibilities. Okay, rubber against iron, and then steel against, I don't know, glass, whatever possibility. A table in the book has, but you will always see that mu k is less than mu s. There may be some special cases where these numbers are really close or same. That's because these are experimentally determined coefficients, and both should be less than 1 in principle again, but you may find some rare cases where it's especially mu s can be greater than 1. Don't worry about those for our class, okay? But these are, the smaller the number, smoother the surface. Like ice should have a 0.03 or something like this, or the joints in your body, okay? Very small number unless you're old, right? But rough surfaces where you want friction means mu s and mu k are close to 1, okay? So the numbers change from between 0 and 1, all right? And as you can see, the static friction force also changes. It depends on what the force you're exerting. A very important point, okay? The static friction is not constant. It depends on the external forces. So this finishes our discussion for this chapter. A very important chapter. The thing we haven't done is an inclined plane. How to draw. No, actually, we didn't. That's not chapter 2. Okay. So we pretty much finished everything in chapter 2. But the applications are endless, okay? I just gave you the basic principles. So I can do some other videos with examples, but most are in the book anyway. So I'm gonna stop here, okay? It's been already almost 2 hours. Let's check the time. It's been a lot of time, so I don't see it here. 2 hours and 19 minutes. Okay, good point to stop. Okay, so till next time, goodbye.